Hello, advanced algebra students. We are going to take a look today at solving higher degree polynomial equations. Last unit we learned you could find the zeros of a quadratic function by graphing, by factoring quadratic formula, and completing the square. So our goal today is to figure out how can you find all of the zeros of a higher degree polynomial. For example, what are the zeros of this polynomial? X to the fifth minus 6x to the fourth plus 20x cubed plus minus 60x squared plus 99x minus the other term there, which I can't see. It says when your polynomial has a degree greater than 2, you want to start by finding the real zeros by graphing the polynomial and calculating the, drum roll, x-intercepts. Okay, because remember the x-intercepts are where our solutions or zeros are. So how many zeros should there be for this polynomial? To figure that out, you have to look at the degree. The degree is 5, which means I should have 5 zeros. From the graph, what are the real zeros? So you have to take a look at your graphing calculator and graph it and solve. So let's type all of that in. So go on to your graphing calculator, graph, and we're going to type that entire equation in. So we'll type in x to the fifth power, and then hit the right arrow, minus 6x to the fourth power, hit the right arrow, and then plus 20x cubed, and minus 60x squared, plus 99x minus 54. And you hit enter, and you notice that it crosses the x-axis at 3 points. And so you want to figure out what are those x-intercepts. It looks like it goes through 1, 2, and 3. Now to double check that, you could either use the menu and choose Analyze Graph and calculate the zeros that way. That would be one way of doing it. Or if you think they're 1, 2, and 3, a quick way to verify that is to just look at the table, Control T. And when you look at the table, you see that when x is 1, the function is 0. When x is 2, the function is 0. And when x is 3, the function is 0. So that kind of verifies that 1, 2, and 3 are your zeros. So we're going to go back here, and we can see our real zeros are 1, 2, and 3. Now, there should be 5 zeros, so we have to figure out what are those other 2 zeros. So now, thinking about what we did yesterday, we're going to use these zeros to break down our polynomial, divide it so that we break it down to a quadratic. That's our goal. So what are the factors associated with the zeros you just found? Well, for when x is 1, the factor would be x minus 1. The second zero we got was 2, so the factor would be x minus 2. And the third zero we saw was 3, so we would use x minus 3 for our factor. How can you use those factors to find the remaining factors? You can divide the polynomial by each factor. To get it down to a quadratic. And then solve. Okay, and so when you solve that quadratic that you get, you can use factoring, you can use quadratic formula, or if there's just an x squared, you can get x squared by itself and then solve by doing square root. Okay, so let's see what happens. So it says find the remaining zeros. Here's our polynomial. Our first zero was 1. So I'm going to take this and use synthetic division. So 1, negative 6, 20, negative 60, 99, and negative 54. You want to write all those terms in a row. And remember, synthetic, you drop down the first number and you get 1. Multiply, you get 1. Add, you get negative 5. Multiply by 1, you get negative 5. Add, you get 15. Multiply 15. Add them together, you get negative 45. Multiply. Then add those together, and you get 54. And then multiply 54 and add, you should get a remainder of 0. Okay, so now we went from a 5th degree. The answer we get here would be 1x to the 4th and so on. But we're going to use these numbers now and use our next 0, which was 2, to break these numbers down further. So I'm just going to use those same numbers and set it up again. Drop the first number down, multiply by 2, add, multiply by 2, you get negative 6, add those together, 9, multiply by 2, 18, add those together and you get negative 27, multiply by 2, you get negative 54, add those together, whoops, that should be negative 54, add those together and you get 0. So now I've broken it down to a degree 3 polynomial. I'm going to use the last real 0 I found, 3, to break this down one more time. And I've dropped down my 1, multiply by 3, add, you get 0, multiply by 3, add, you get 9, multiply by 3, add, you get 0. So the remaining factor I get is 1x squared, or just x squared, plus 0x, so I don't even need to write that, plus 9. So factored form, I have this, times this, times this, times this, equals 0, because we're looking for the zeros. So we already know 1, 2, and 3. So now we just need to solve the x squared plus 9 to see what my last two zeros are. So you can take this remaining factor and set it equal to 0 and solve for x. Now notice I don't have an x term in here, I just have x squared. So this time I don't need a factor, I don't need to use quadratic formula, I can just get x by itself. Minus 9 from each side, and that's gone. So then I get x squared equals negative 9. To get x alone, you have to undo the square, so square root each side. Square root of x squared is x. The square root of negative 9, remember square root of 9 is 3. The square root of negative 1 is I. You get 3i, and that's plus or minus. Remember, both positive and negative. So your 5 solutions are, or your 5 zeros are 1, 2, 3, positive 3i, and negative 3i. And you had, the degree was 5, and we ended up with 5 zeros. So that is it. Whoops, I missed a page. So notice complex roots will always come in pairs. In that last problem we had positive 3i and negative 3i. They're always conjugates of each other. A plus bi, a minus bi. They're called conjugates when they're in that form. So conjugate pairs. Okay, so you will never get, you can either get no complex roots, 2 complex roots, 4 complex roots, never an odd number. They always come in pairs. How can you verify that a number is a 0 of the polynomial? So just like we've done before, you can divide using synthetic division or long division, and if the remainder equals 0, it's a 0. okay? Or you could plug in the number for x in the equation and see if it equals 0. Okay? It should equal 0 for it to be a 0. All right, let's look at an example. So consider this function, 2x cubed minus x squared plus 18x minus 9. Verify that 3i is a 0. So I could try to do synthetic, but it might get a little bit tricky with the 3i. It might be easier in this case to show that it's a 0 by plugging in 3i for x and showing that it equals 0. So when I plug it in, I get 2 times 3i to the third power minus 3i squared plus 18 times 3i minus 9. Okay, so if you simplify, 3i to the third power is 27i cubed. 3i squared is minus 9i squared. 18 times 3i is 54i. And minus 9. Okay, so we need to simplify this I cubed. Remember that I cubed is equal to I squared times I. Right? That would be like I to the third power, because there'd be 3 i's being multiplied together. And I squared always equals negative 1. So this becomes negative I. So I can replace this part here, well, 2 times 27 is 54 times negative I. And this again is I squared, so I squared equals negative 1. So this really becomes positive 9. This is positive 54i and then minus 9. So if I simplify, 54 times negative I is negative 54i. That's going to cancel out with the positive 54i. This is positive 9 minus 9, so they cancel out. So it equals 0. Therefore, 3i is a 0. And it says find all the zeros. So I know that if 3i is a 0, and my imaginaries always come in pairs, 3i is a 0, then negative 3i has to be a 0, because they always come in pairs. The factors associated with those zeros are x minus 3i times x plus 3i. Now doing synthetic with a 3i is a little tricky, so it might be better to multiply these together. And if you multiply those two terms together, what's nice about that with the conjugates is your I terms should cancel out. So you get x minus 3i times x plus 3i. If I multiply it together, I have x squared minus 3ix plus 3ix minus 9i squared. So these will cancel out. And minus 9i squared is like saying negative 9 times negative 1, so plus 9. So when you multiply this together, you get x squared plus 9. And that is a factor of my original polynomial. So therefore, I could divide with long division my 2x cubed polynomial by x squared plus 9 to see if I can get my remaining factor. So let's do that. We had 2x cubed minus x squared plus 18x minus 9 divided by x squared plus 9. So if I plug all of this in, or if I divide, x squared times 2x would equal 2x cubed, so I put 2x on the top. And that is 2x cubed. 2x times 9 is 18x. So when you subtract, these cancel out and these cancel out. You have negative x squared minus 9. So what do you multiply x squared by to get negative x squared? You'd say negative 1. Put that on the top. Multiply, you have negative x squared, and negative 1 times negative 9 is negative 9. When you subtract, both cancel out and you get a remainder 0. So 2x minus 1 is your remaining factor. So if you set each of these equal to 0, if I solve this for x, I get 3i and negative 3i. So if I solve this for x, just set that equal to 0 and solve. Add 1 to each side. You get 2x equals 1. Divide by 2. You get x equals 1/2. And that is your remaining solution. 1/2, 3i, and negative 3i. Those three solutions. Okay, so what if you're just given this equation with nothing, and it just says find all the roots? Well, if you're not given anything, then you should go immediately to your graphing calculator, graph it, and look for your x-intercepts. So that's what I would do. Type this into your calculator and look for your x-intercepts. So I'm going to just make a new document, add graph, type that all in, 3x cubed plus 5x squared. Oh, I forgot to do the right arrow. So make sure you do the right arrow before you do plus 5x squared. Minus 25x. Oh, I forgot the minus 15x. Okay, so when you graph it, you see 3 real zeros. And since my degree is 3, those are the only zeros I have. So it's just a matter of going through. I'm going to move this label a little bit out of the way. And finding those x-intercepts. And they don't look like they're at whole numbers. So I would use the menu button, Analyze Graph, and pick 0 to find my x-intercept. So the one over here is at 2.24. Okay, menu, Analyze Graph, 0. Pick this one right here. You got to put the line on either side, click it. There's that one. And then the last one, menu, Analyze Graph, 0. Over here, click on either side. That one kind of got jumbled up there. So there are your 3 zeros, positive 2.24, negative 1.67, and negative 2.24. Those are your 3 solutions for that problem. Okay, so where were we? So that was a solution there. And then here it says the fundamental theorem of algebra states this right here. A polynomial of degree n will have n roots. This includes the repeated roots and the complex roots, the imaginaries. So here, when I'm looking at this equation, my degree is 4, so I should have 4 zeros. That's what the fundamental theorem says. Name the zeros. So if I want to name the zeros, they don't give me anything. You got to go to your graphing calculator, type it in, and look for those zeros. I'm going to let you do that one on your own. But just know, when you type it in and look for those zeros, there were 4 real zeros. So when you're looking for those x-intercepts, they should be negative 5, negative 1, 1, and 2. If it asks you to write the polynomial in factored form, you would write x plus 5, x plus 1, x minus 1, and x minus 2. Those are your solutions. And that's it. Have a great day.